We ended class today with a look at a proof for the Pythagorean theorem. We started with 4 congruent triangles with side lengths A, that's the longest leg, B, the short leg, and C, the hypotenuse. And we cut each of the 4 triangles out and arranged them in this empty space here, along with exercise 1-9-2. I take it back. It is exercise 1-109. And the first configuration of these 4 congruent triangles looks like this, where we are asked to find the area for the unshaded region. So that's the square in the center. Each of these sides of the unshaded square has a measure of C given by this side length here, C and C. So we can call this C squared. Now, how do we know that each of these is a 90-degree angle? Well, don't we know that the 2 acute triangles of any right triangle must sum to 90? Because the right triangle has a sum of 90? And aren't these on a line or straight angle that has a measure of 180? So the whole angle along the edge is 180 degrees, and we're subtracting the 2 acute angles of a right triangle, so we know that this corner has a value of 90 degrees, and this corner, same thing, value of 90, value of 90, and value of 90. So we know it's a square because it has 4 congruent sides, each of length C, and it has 4 right angles due to the subtraction property. So we can call the area of this square C squared. And we can also rearrange the triangles as shown in exercise 1-109. But now the area of the unshaded region has a side length of A and A. So we can call this square A squared. And this unshaded area has side lengths B. So we can call this area B squared. So the area in this representation of the unshaded region is equal to A squared plus B squared. But we also know that the area didn't change. So area being a conserved quantity, we haven't overlapped any of these triangles. This is a proof for the Pythagorean theorem that the area formed by each of the legs of a right triangle, when added together, is the same as the area formed by the hypotenuse of a right triangle. And that allows us to use the Pythagorean theorem to find missing side lengths, to confirm certain triangles are indeed right triangles. And that's what we're going to use the Pythagorean theorem for. Let's take a look at an animation, which is another proof for the Pythagorean theorem. So in this animation, we have a right triangle with side lengths A, B, and C. And parts of area B squared along with area A squared are being reassembled in the area that has C squared, that has area C squared. Nothing's overlapping. So this is another proof for the Pythagorean theorem. What is the area of this gray region? Let's check out that animation. Here's the arrangement you made before. So let's take a look at the examples in 2-111. The first example is a triangle with legs marked 4 and 5. So go ahead and draw that triangle. Mark the right angle. X is the hypotenuse. And we use the model triangle ABC where C is the hypotenuse. So here, let's replace A and B and C. 5 squared plus 4 squared equals x squared. And we know the square of 5, we know the square of 4. We know how to add 25 and 41. Sorry, 25 and 16. And we're looking for the square root of 41 as a value for x. Now, when we're solving algebraic equations with a square root, we look for the positive and the negative. Do we need to worry about the negative value for x in this case? It's a side length. It represents distance, so we can disregard the negative square root. Now let's talk for a little bit about exact values and approximations. The square root of 41 is the exact value. That matters. You will be asked to determine the difference between the exact values and the approximate values. Now, something happened to most students in the 5th and 6th grade when we introduced the calculator. You have come to believe that this approximation that you get when you push the square root of 41 in your calculator and it spits out 6.4, you will have come to believe that that is very exact because it has a decimal value. In fact, that is the approximate value. If you square 6.4 in your calculator, you get something close to, but not exactly, 41. When you square the square root of 41 in your calculator, you get exactly 41. So concentrate on the difference between the exact value and the approximate value and practice giving the correct one. In the second example, go ahead and draw that next triangle. We have an 11 and a 7. Only the 11 is in C's place, or the hypotenuse's place. We're missing Y. So we're going to use the Pythagorean theorem that says that the squares constructed on the legs of a right triangle will equal the square constructed on the hypotenuse. So 7 squared plus y squared equals 11 squared. 49 plus y squared equals 121. Subtract 49 from both sides. So the important part here is the setup. You already know how to solve Simple equations. 121 minus 49 is 72. Taking the square roots of both sides, we're left that y equals positive or negative 72. Sorry, y equals the square root of the positive or negative square root of 72. We don't need the negative square root, so we're only worried about the principal root. The exact value is the square root of 72. The approximate value, and you should give both unless you're asked for one or the other, when calculated by your calculator, is approximately 8.49. In 2-111C, I'm asked to determine the perimeter of the rectangle shown at the right. Well, I have in 6 squared plus b squared equals 15 squared situation. 36 plus b squared equals 225. B squared equals 225 minus 36. So b equals the square root of 189. So to find the perimeter and the area, I simply perform the substitutions in the two different formulas. Area for a rectangle equals square root 189 times 6. These are square millimeters. Area is 82.49 square millimeters. Perimeter then is square root 189 plus square root 189 plus 6 plus 6. Perimeter then, and I should have put the approximation in area. Perimeter then is approximately 39.5 millimeters. Two 112, the Garcia family problem, will be assigned for performance tonight.